Can you see my screen? Hello. Can
Yes, sir.
Okay, great. All right. So far we had been we are almost like in the finish line of our discussion on the simplex algorithm. So there are a few things to clarify. Um, so let's start our discussion with something which we didn't finish last time about neighboring vertices. And that was essentially translating between like the geometric picture of neighboring vertices where essentially we had like a one-dimensional face which we call an edge, and the endpoints are vertices, and those are known as neighboring vertices. And the example we had in mind was, let's say we join two tetrahedron like this, then these two are neighboring vertices but these two are not neighboring. Okay, so that was the geometric picture we had in mind. And then a computational picture we had in mind was based on like pivoting. Essentially you have this column vectors of A, which leads to a feasible solution known as the basic feasible solution with respect to that basis. And all you do is remove one of those column vectors and add another so that it still becomes a basis. And then those corresponding, the claim is that those two corresponding things are neighboring vertices. So we want to see this translation between the geometric picture and the computational picture first. And in fact, this is very nice because it almost will tell you that just starting by geometric intuition, you can reach the definition of a basic feasible solution. Otherwise, it looks like you're taking a rabbit out of a hat. You just like one day decided you want to define things like basic solutions, basic feasible solutions, and so on. But once we go through these few next propositions, we'll see how naturally that definition should come into mind. Or in other words, you can say you can also discover basic solutions or basic feasible solutions. All right, so let's start with definition of neighboring vertices. So first of all, we need a polyhedron. So let P be determined by these finitely many linear inequality constraints. Okay, so this be a polyhedron in Rn. And then two vertices of P. So two vertices of P are said to be neighboring. So let's denote them by V1 and V2 are said to be neighboring vertices if they're the endpoints of a closed one-dimensional face. Closed one-dimensional face of P. And if we are thinking in terms of the matrices A and this vector B, essentially, in other words, so we had proved one of the results concerning this P and vertices of P is that every vertex of P is determined by n many linearly independent constants, and where these inequalities are actually tight at that particular V. So, and here, so using that description, so each of V1 and V2 has such a description. You have n linearly independent constants where V1 is tight, and you have n linearly independent constants where V2 is tight. So in essence, if V1 and V2 will be neighboring, if the intersection between those n constants for V1 and n constants for V2 is a set of size n minus 1. So there are n minus 1 linearly independent constants. So n minus 1 out of those constants, which are common for both V1 and V2. So let me just write it out. So in other words, V1 and V2 are neighbors if there are n linearly independent constants amongst ax less than equal to b, amongst ax less than equal to b, which are tight at v1. So that's just telling us that v1 is a vertex. Um, And similarly, and n linearly independent constraints again amongst ax less than equal to b tight which are tight at v2, and both of these set of constraints have an intersection of size n minus 1. And of course at those n minus 1 constraints both v1 and v2 are tight at those constraints which are tight at v2 such that precisely n minus 1. So if you chose the like same set n, then of course you'll get the same vertex. So those will not really call neighboring vertices, such that precisely n minus 1 of those tight constraints are shared by v1 and v2. So this is the geometric picture I was saying, shared by v1 and v2. And why is this a geometric picture? That's because every single inequality constraint is supposed to give you a closed half space. So essentially the boundary is a half plane, is a hyperplane. So the boundary is a hyperplane. And this part is the closed half space. So let's say this is something like ai vec transpose x is less than or equal to bi. So this denotes the ith row of this matrix A. And if I take, and of course, all these vertices must lie on the boundary. So this shaded region doesn't really count. So all we care is about equality here on the boundary. And if I take two hyperplanes and intersect, two generic hyperplanes, and I said the rigorous way of talking about generic hyperplanes is linear independence of the AIs. So A1 and A2 will generate two generic hyperplanes if A1 and A2 are linearly independent. Similarly, if you have n of them. So if I have two generic hyperplanes, that means they are not parallel, then their intersection will be one dimension lower. And similarly, if you have n many, then it will be like, or k many, then it will be k dimensions lower. Of course, you have that restriction that k must be less than the dimension of Rn, where we're operating in that real vector space. So if we want a zero dimensional, uh, so if we intersect n of linearly independent things, then what you'll end up with something is something which is zero dimensional. That will in fact turn out to be the vertex. All right. So this is what I will call the geometric picture. And then I'm going to give another definition. So this, I mean, the connection is, of course, is something which we have seen. We had proved that in LP in standard form, like for the feasible set, like the basic feasible solutions are precisely the vertices and vice versa. Vertices are precisely those basic feasible solutions. But let's keep that as a result. So for now, let's look at a definition. Now let's say you have this matrix A and LP in standard form. So AX equals B, and you have all these sign constraints. So two basic feasible solutions of this standard, like polyhedron in standard form, so to say, because here the cost function is not like really playing a role. So I'm not going to talk about a linear program, but rather let's call this a polyhedron in standard form. So two basic feasible solutions, say let's say corresponding to basis B1 and B2. So corresponding to basis B1 and B2 are said to be adjacent. So let's call them adjacent. We could also call them neighboring. So depends on, so neighboring, I'm trying to invoke a geometric picture. Adjacent, I'm just trying to invoke some sort of combinatorial picture. So they are said to be adjacent if cardinality of B1 intersection B2. So typically we have ordered bases. So for them, so you treat them as a tuple. But for this purpose, just pretend that like the ordering doesn't matter. So if I take the intersection of this B1 and B2, this is precisely equal to n minus 1. So this is where I will call two basic feasible solutions to be adjacent. And as you can guess, the whole point is to relate these two notions, this computational notion, because you're choosing certain indices from like between like you're choosing m things from n columns. You're choosing m columns which are linearly independent. That is giving you a basis, and you're just removing one of those columns and adding something else, and still making sure that these m resulting m columns are linearly independent. So these will correspond to adjacent basic feasible solutions. Yeah, the corresponding basic solutions will be adjacent. Okay. So now we'll prove somewhat of a computational lemma, but it is very easy to see, very basic linear algebra. So let's say we have this matrix A and A. Assume A is full rank. So look at these two matrices. So what is this? This is a m plus, or maybe I should write n plus m by n, just to emphasize the sign constants are in the beginning. So this is n plus m by n, and this is m by n. All right. So let's say J1, J2, Jm are distinct members of 1 to n. So let me use this notation. This is pretty standard notation in combinatorics. This means the set 1 through n. Okay. So let J1, J2, Jm be distinct members of n. So here, so the lemma says you take these columns aj1, ajm of A. So these are, so this is a basis for Rm if and only if. So here we are talking about columns, right? Aj, these are columns. So A has been written as A1, A2. And remember the previous class, there was some confusion, like we could not finish the argument. And the confusion was between how to go from, because the constraints seem to be about row vectors. But somehow talking about basic feasible solutions is all about column vectors. So how do I translate my observations from this to that? So this is the lemma that will do it. So AJ1, AJM is a basis of Rm if and only if the m rows, so take the rows of A, so those are all linearly independent. We have chosen, by the way, like when we talk about standard form polyhedron, we always assume if it is non-empty, then we can always assume A is a full rank by just doing Gaussian elimination and row echelon form and so on. Okay, so the m rows of A plus the n minus m rows of this In, which are given by, so let me just write Ej transpose. Ej is the standard column vectors where J does not belong to this set. So, I mean, you can always write it as set capital J, but essential idea is you include all the rows of A and n minus m rows of In. So which n minus m rows of In? This, the Ej transpose. So these anyway, this is an identity matrix. So these are just 1, 0, 0, 0, 1, 0, 0, and those. So you remove all the rows that correspond to J1 through Jm. So whatever remaining, you have n minus m. So total you get n. Uh, yeah. So if and only if these n rows are linearly independent. So this is where, so this is a complete sentence now. So let me restate. So if you chose some indices J1, J through Jm, perhaps you can, sorry, is there a question? Okay, if not, so let me continue. So you chose this indexing set J consisting of m distinct elements from 1 to n. So my claim is, so this lemma states that aj1, aj2, ajm is a basis of Rm. In other words, I could replace this by saying this is these columns are linearly independent if and only if I'm translating it about some statement about rows of this big matrix. The if and only if the m rows of A, you are including these things, plus the n minus m rows of this matrix In, which are given by all those indices not contained in this J. So if these rows are linearly independent, these n rows are linearly independent, then these m columns are linearly independent. So numbers are different. Here you have m columns, here you have n rows. So let's try to prove this lemma. Okay. So equivalently, we'll just proceed very slowly because this is quite important. So equivalently, what we want to show is aj1, ajm are linearly independent. I mean, this is m things in Rm. So linear independence is exactly equivalent to saying it's a basis. So this holds if and only if m rows of A, means all rows of A plus n minus m rows consisting of Ej where J does not belong to this indexing set J of In. So all these combined are linearly independent. So this is what we want to prove. Again, equivalently, this is all very obvious, but I'll state it anyway. So since this is about equivalence about two statements, I can replace it by a negation. I want to prove P if and only if Q. I can just prove not P if and only if not Q. That suffices. So what I really want to prove is these are linearly dependent if and only if the m rows of A plus the n minus m rows is a transpose where J is not in this J. Here this J is in J. Here you're saying J is not in J. So these rows of so treat them distinctly. M rows of A and n minus m rows of In so are linearly dependent. So this is what we'll be proving now. All right. So we'll prove the first implies the second. Okay, let's go in this direction first. So assume that aj1, ajm, these are linearly dependent. So we are denoting this matrix by aj. So these are all the columns corresponding to the indexing set j. So aj is not invertible because they're linearly independent. Okay, so if so since aj1, ajm are linearly dependent, aj is not an invertible matrix. Then there is some so there is a null space. Even its transpose has a null space which is non-trivial. So in fact I can multiply a row vector. So I have these things aj1 through ajm, which I can multiply with aj to be 0, where this vector aj1 through this row vector is not equal to the vector 0, 0, 0. So there are some coefficients aj1 through ajm, not all 0, so that when I multiply this with aj, this is equal to 0. Okay. So this will yeah. So this now what happens is there are remaining like columns of A, right? So A essentially comprised of AJ. So A I can think of as AJ and AJ complement. So what I know is if there is some row vector which I multiply, this part will vanish. Okay. So now I want to expand this row vector and take the IN matrix into account and ensure that I have a non-zero vector such that that times the INA matrix is also 0. Okay. All right. Okay. So what happens when I multiply aj1 through ajm with the matrix A? What happens is aj will give me 0, and then I have something, let's say A vec transpose, aj vec transpose, aj complement. So I have something here. Now look at what rows we have chosen from IN. We have only chosen those rows where J is not in J. So rest we have discarded. So essentially, this will look like zeros because for the ones corresponding to J, we have chosen to be, we have discarded those EJ transpose. So here you have IN minus M. So this is the matrix we want to show that this is actually not invertible. Okay, so we have this. Sorry. So this is the matrix we have 0, IN minus M, I have AJ, AJ complement. This is just a representation of A. I'm just saying A. Note that I have shuffled the columns, like, so strictly speaking, I have to be very careful with notation, but it's understood. Like here also I have shuffled the columns and put them in one side. So this corresponds to J complement. So this is essentially the matrix of the second part. So this corresponds to the matrix of the second part. And I want to prove that the rows here are not linearly, they're linearly dependent. So essentially I want to find a row vector which I multiply on the left. Then what I will get is this will be equal to 0, a non-zero row vector. That's what I want. So first of all, what I will do is for the j indices, I'll choose aj1, ajm, so that this part will vanish. And then for the rest of this, I know that this is not really a full rank matrix, right? Because what is the dimension of this matrix? This in minus m, so you have n minus m linearly independent things here. The number of columns is n minus m. So the rank of this matrix is n minus m, but the number of rows is in fact n minus m plus m, it is n. So this matrix, so I n minus m aj complement is not of full rank. That is very clear. It has, in fact, it is rank. Sorry, it is a full rank. Okay, let me not say something ambiguous. So it has rank n minus m, but the number of rows, so number of rows is n, which is strictly bigger than n minus m. So these rows must be linearly dependent. But those coefficients, whichever will determine that linear dependence, will be independent of these coefficients, right? So I mean, you may choose them all to be 0. So you may choose, but then all of these coefficients are still non-zero, right? Okay, let me redo this. So first what I'm doing is I have this 0, I n minus m, aj complement. Then I'm doing uh, some operations here, some like Gaussian elimination. Then I'm reducing it to 0, and then I have a column of zeros, let's say, because this is not a full rank, aj is not a full rank, it is not invertible. And then I have some entries here. What I've done is an invertible operation, right? So in any case, so that will not be an issue. So aj complement has also changed. So it has changed to something else. So let's say we have done some elementary operations, x. So this has also changed to x aj complement. So now for this, I have a row vector. Okay, I mean, this should be fairly straightforward, I think. Yeah, I mean, it's just a matter of transforming this aj complement and then choosing the vector that you want to choose to make it equal to 0. I want to fill the rest of the entries. So this is aj. I want to fill in the entries aj complement, such that what you'll have is something which is 0. Right, yeah, yeah. So hmm. Yeah, so here again, you choose some vector for aj complement, such that this part will vanish. So this will be equal to 0. So this vector aj complement times I n minus m x aj complement is equal to 0. So this is a non-zero thing. And um, yeah, Okay, let's just look at this a little bit more. So I have AJ and AJ complement. And this I'm trying to, so this part, or rather, let me put it this way. So this is 0. We know AJ transpose times AJ is equal to 0. So this part is 0. And then we want to, essentially AJ we have figured out. That is the AJ1, AJ2, that vector. So that we have figured out. What we really want to figure out is AJ complement. So we want to find something so that AJ complement plus AJ AJ transpose AJ complement. Okay, yeah. So yeah, this is straightforward. So what is AJ? So first of all, you have already chosen your AJ, like I said. So this is the, since AJ is not invertible, there is some row vector so that AJ1 through AJn times AJ is equal to 0. So you just choose that. Now essentially what is left is to choose the rest of that vector. So I want to make this equal to 0. But what is this AJ? Yeah, so this is AJ complement. You'll get some vector. Doesn't matter. You'll get some rows. So essentially, you'll get a vector in R n minus m. So this will be a row vector in R n minus m. All right, and that is in the span of this I n minus m. So whatever coefficients you get here, in fact, you can just read off what your AJ complement should be. You can just read off from this thing. It will just be negative of that. So it should be minus AJ times AJ complement. All right, so let me just write AJ vec transpose. So this is a n minus m times 1, 1 times n minus m matrix. So this will be nothing but minus of AJ complement. So this is 1 by m, and this is m by n minus m. So yeah, all right. So this finishes the proof of one direction. So you essentially what you have done is built up this vector A. So A is non-zero because already a subpart of it, the AJ part of it is non-zero. And when we multiply it with this big matrix, In minus M and A, so then it is giving you 0. So that means this matrix cannot have all the rows to be linearly independent. So this proves the indication that if AJ1, AJM are linearly dependent, then the M rows of A and the N minus M rows consisting of this EJ transpose, where J is not in this indexing set capital J, these are linearly dependent. So now we have to do the other direction. Okay, so this direction. So we start with the assumption. Yeah, so this 0, you have AJ complement, In minus 1. So rows of this matrix are linearly dependent. So this is the assumption we're starting with. And then we want to prove that this cannot be invertible. This is something basic from matrix algebra. You can actually, so AJ is what? It's yeah, right. So just take a vector A such that A transpose of this thing A0 I n minus m AJ. This is actually the easier direction. So this is equal to 0. So it's in fact the vector 0. So in that case, what you have to do is just look at the AJ part. So essentially, directly from computations, what you have concluded is so this is nothing but aj plus aj complement. So this is equal to 0. Reform. Okay. So these rows are linearly dependent. Right, right, yeah. So yeah, yeah. So yeah, this is just stupid. This is actually pretty straightforward. So these rows are linearly dependent, meaning there are some elements such that when you take the non-trivial linear combinations of these row vectors, you get the zero vector. That means in particular, the linear combinations corresponding to this must also give you zero entries. So A1, like the linear combination of these rows should also give you zero entries. So that means the rows are not linearly dependent in AJ. That means the columns are not linearly dependent. But there is one caveat here. What could happen is the corresponding J's could be zero. Uh, yeah, so just looking at these columns, just looking at J1 through Jm, the ones corresponding to J, we have AJ1 through AJM acting on this matrix is equal to 0. So this part is clear. Like, assuming you started with the vector A such that A transpose acting on this is equal to 0. But the only problem is what could happen is all these AJ1s could be zeros. Then this does not really prove anything. So, but that is not true. So not all of AJ1, AJM can be equal to 0. So why not? Because if yeah, if AJ1, yeah, right. So this is where you'll use the fact that A is a full rank, because AJ1 essentially they correspond to these parts. So if AJ1, AJ2, they're all zero, that means when I'm taking linear combination of these rows, then you're just getting zeros. So that means AJ complement, yeah. So this is where we're using this fact, times A is equal to 0. That means this must also be the zero vector because A is full rank. In fact, the row rank is m. So you must have this. So essentially, if this is the zero vector and this is zero vector, then like by our choice, originally A is not zero, right? A is not zero. And AJ complement has to be zero because A is full rank. So this means AJ is not equal to zero. So this finishes the proof. So here we had to use this crucial fact that A is assumed to be of full rank. Okay, so both directions are proved. So since we fumbled around a little bit, let's look back at the lemma once again. So what it's trying to say, it's just saying that if I choose an index set of size m in 1 to n, and if I look at these two matrices, one is in padded with A. So when I'm putting together all the sign constants and everything, this is what the matrix will look like when I'm generating that polyhedron. So these represent the equality constants and these represent the inequality constants. And here A, I'm looking just at the columns. So here I'm saying AJ1, AJM is a basis, or this is linearly independent, if the m rows of A and the n minus m rows of In are linearly independent. Okay. So based on this lemma, we'll look at a couple of corollaries, which will look very familiar. So corollary 1 of this lemma. A vector V in F, so this is a feasible set of a linear program in standard form, is a vertex if and only if V is a, so this theorem we have already proved is a basic feasible solution, but we'll see it as a corollary of this result. If and only if V is a basic feasible solution. So what is a vertex? So you have to look at this polyhedron, right? So let me just, so proof. So essentially we have this INA acting on X is bigger than equal to something which looks like 0, 0, 0, and at the end you have a B, and all of these uh, so okay, so let me just say you have INAX is bigger than equal to 0 if I'm looking at the just the sign constants, and here it is equal to like B minus B, let's say. All right, so now in order to be a vertex, n of them have to be like n linearly independent elements here. So for a vertex V, I must have n linearly independent constants which are tight. Independent constants which are tight at V and containing the constraints Ax equals B, containing the constant. So any vertex has to satisfy this. So these are already tight constants, right? So these m constants have to be there. So the only option you have for a vertex is to choose n minus m of these constants which are tight. And what does tightness mean here? It just means x is equal to 0. So you have n minus m of those variables where like the value of x is 0, and this is beginning to look very familiar. Like it's beginning to look like which of these columns correspond to basic and non-basic. So it's beginning to look very familiar. So if V is a basic feasible solution, then whatever indices you set to 0, then whatever is remaining is your J. Because remember, like J complement is what we just removed. The rest are linearly, whatever is in J complement is in fact linearly independent of A. If you include something in J, then it will be linearly dependent. So based on that, so that proves this fact. Based on this intuitive description I gave in this beginning of this lecture, that a vertex is determined by hyperplanes, like linearly independent n many hyperplanes. Okay, so this is let's say it's a new proof of this fact which we have already seen. There we actually gave a more direct proof. We used the definition of a vertex, saying that you are not able to perturb the vertex in a linear fashion and still stay within that convex set. Or in other words, you cannot write a basic feasible solution as an average of two distinct things in the feasible set. But here we are giving a more computational way of looking at it. Okay, and then corollary 2 is about neighboring vertices. So this is the one that this is the picture we wanted to clear up last time. So V1, V2 in F of LPS are neighboring vertices if and only if they are adjacent basic feasible solutions. Neighboring vertices if and only if they correspond to adjacent basic feasible solutions. Okay, and the proof, again, you just have to look at the description. The lemma essentially gave you a one-to-one translation between talking about linearly independent rows, like what constants can be tight, and how it relates to columns being independent, the corresponding indices. So J1, J2, Jm. So let's meditate on that statement again. So you choose these indices J1, J2, Jm, and those exactly are the indices that you're ignoring in the row vectors. So you're looking at J complement. So not in J1, J2, Jm. So how do you translate? If I give you n constraints which are tight and containing all the constraints Ax equals B. So what will happen is then you have to choose n minus m many here. So whatever you choose here, choose its complement and choose those columns. So those columns must be independent. And as it turns out, that since the constants are tight at those in those elements of J complement, you have to set xj equals 0 for J complement. And for the rest, you know how to solve. You look at this padded matrix aj1, a2, ajm. You take the inverse and multiply it with B. then you get a basic feasible solution. Okay, so this is the translation. All right, so and the reason we cared about neighboring vertices is because the way simplex works. So let's do some sort of flow chart of simplex. So simplex algorithm. So essentially, you want to solve a linear program. So first you determine whether it is feasible or not by some means. So either you can just immediately, in fact, we'll do it at the end of the class, we'll figure out a way to check whether an LP is feasible or not in the standard form. Once we transform it into standard form, we can immediately check. But as of now, like a lot of the times it is immediately clear. Like you know one instance where like the constraints are satisfied, and that is you're looking for the best possible. So in real life, it is almost always very clear, at least one example of a point in the feasible set. Like I was saying in the first lecture example was that you're using fertilizer, pesticide. You can always choose to not to do anything with your farm. So 0, 0, just put zeros everywhere. Then that is still feasible. But in general, if you have a very complicated problem, you want an algorithm to determine this. So we'll state that at the end. But if it is feasible, then you find a basic feasible solution. That also we have not done yet, like how to find a basic feasible solution or find a vertex. And then once you have found a basic feasible solution, one is it is unbounded. It is possible that the linear program is unbounded. Then also you're not very interested. Anytime you move to the right of the tree, you're not like this is like an ill-posed problem. That's the term I have been using. Or what you can do is navigate. So this is where the simplex comes into play. Simplex algorithm. Move to cheaper basic feasible solution. And then you keep doing that. So keep doing that. So keep doing this process until it ends, until termination, and it will terminate. There is a small step that will remain, but there are finitely many vertices. The only problem that can happen is you cycle amongst the vertices of equal cost. So that is something that can happen. But or you just stay put. You don't really move. You're changing um, your indices. You have some degenerate solutions, degenerate vertices, but you're just sorry, not degenerate vertices, but rather you have certain like degenerate like basis for your basic feasible solutions. And then what you do, you're changing your basis by pivoting, which is the computational method for navigating from one vertex to its adjacent vertex or neighboring vertex. But what might happen is that algorithm may stay put. You just stay in the same vertex. So that might cause some problem. Like the algorithm might not halt or terminate. So those are the things we have to take care of. But this is the step we are talking about right now. You have a basic feasible solution. You want to move to a cheaper basic feasible solution, or in geometric terms, you are at a vertex. You want to move to a cheaper neighboring vertex. All right. So just as a reminder, what had we done? We were talking about pivoting. So pivoting was the strategy of. So here, this is the pivoting. Basic feasible solution, move to cheaper basic feasible. So strategy of moving to a neighboring basic feasible solution of cheaper cost. And the final thing we had done in the previous class. So a basic feasible solution corresponds to an ordered basis. So what we do is, like we had been representing those using some tableau. So just to remind you, the tableau corresponded to, you have this matrix A, you put B here. And then typically to make life easier, if you have this J1, J through Jm such that these AJIs are linearly independent, you do some row operations and convert them into identity matrix. Like EJ1 is E1, EJ2 is E2, or rather AJ1 becomes E1 and so on. And then it becomes very easy to read off how to pivot. So for pivoting, you have to choose a non-basic column. One basic column will exit, a new non-basic column will enter. But to make the appropriate choice, so the cost function has to come into play, because there are two factors in the traversal of this vertices. First of all, you have to go to a neighbor. That means choosing a non-basic column, and then it has to be of cheaper cost. So for that, we had put this cost function here. We had talked about the modified cost. We had a formula for the modified cost, and we wanted the modified cost to be negative, because then that would mean if I choose that basic column, the modification that I'll get, Cj minus this Cbi Xij, where j is the non-basic column you're choosing. If this is strictly less than 0, introducing j into my basis actually reduces my cost. So that's why you had this updated tableau where we are putting these cost functions on the 0th row, so to say. And then after this modified cost, we're looking at the cost which is strictly negative. So the basic columns, you'll get zeros here. The non-basic columns, you look at all the entries where the cost is strictly negative and choose that non-basic column. So let me again rewrite that. So find the column J. You can refer to your previous lecture notes. So I'm just saying it verbally, a lot of things. So we have to find a column J. So to pivot to that column J, whose row 0 entry, so that is corresponding to the modified cost. So row 0 entry is strictly negative. If there is no such column, what could happen is all of the columns have cost bigger than equal to 0. All the modified costs are bigger than equal to 0. So if there is no such column, we are done by a previous theorem. We had proved that if Cj is bigger than equal to 0 for all j, Cj bar, Cj bar is bigger than equal to, that the modified cost is bigger than equal to 0, then whatever vertex or whatever basic feasible solution you are at is already the optimal solution. So that's something we had proved. Okay. So the algorithm is terminated if this cannot be done. But if it can be done, I will choose such a column j. Then next what I will do is compute this thing called theta naught, which is minimum of this xi0 over xij. Remember, j has already been chosen in step 1. So j chosen in step 1. So j is fixed, I is varying. Over what? Over all those indices from 1 through m, where xij is strictly bigger than 0. So of course, we are here assuming this is non-empty. So what if it is non-empty? That's what we're going to answer next. So for the moment, let's assume this is non-empty. So this is the theta naught we are choosing. Then 3, we are finding. So step 1 essentially told you which column which will exit, which column will enter. So column J we will add to our new basic new ordered basis corresponding to basic feasible solution. But what will exit? Which column from your ordered from your basic columns will exit? So that is given by part 3, and for which we need part 2. We need theta naught to determine this. So find an L such that theta naught is equal to xl0 divided by xlj, and xlj is strictly bigger than 0. So that is kind of a given. So now what we do is pivot on the ljth entry, or in other words, column J enters and column BL. So in the ordered basis, this is the lth column. I mean, things can be interspersed, but ordering matters. So I want to stress that. So column BL leaves. So again, you end up with m linearly independent columns. That is your new basic feasible solution. Okay. So still there is a gap. This is the gap we are going to fill right now. So here we have assumed it is non-empty. So what happens if it is not non-empty? It turns out that if it is not non-empty, that means it is empty, then our LP is unbounded. It is ill-posed. Okay. So in that tree, if you remember this picture of the tree, so we'll navigate here and terminate. So theorem, if Cj bar is strictly less than 0. That's step 1 determined that there is some j, so that Cj bar, the modified cost, is strictly less than 0. And Xij, the corresponding things in that in the jth column of the matrix X. So if Xij is less than or equal to 0 for all of these i's, for all I between 1 and m, then the LPS instance is unbounded. Then the LPS instance is unbounded. This is not very surprising. Actually, when we are trying to figure out theta naught, we are trying to guess what theta naught should be. We had noticed that if XLJ is less than or equal to 0, you can choose theta naught arbitrarily large. Then you'll still remain feasible. So that is not an issue, because when you're multiplying theta naught with Xij and putting a minus sign, it is always going to be positive. So that observation we had made in the very beginning when we're talking about finding theta naught. But what so there it was just about feasibility, but here it's about cost. So here we want to show that the cost function in fact can be made arbitrarily small. So that is the main difference here. So proof, so let theta be something which is bigger than or equal to 0 and x naught be the current basic feasible solution. Okay, and now define w theta to be x naught. So this is our original thing, and then I'm navigating in this direction, alpha 1 3 alpha n theta, where alpha k theta, that is the kth coordinate here of this perturbed vector, is minus theta xij if k equals bi, because essentially we did x naught I minus theta xij. So this is just saying that in which direction we're moving, with which direction we're perturbing this current BFS. So to that neighboring vertex, if I join these two neighboring vertices, what will be that vector? That direction is determined by that alpha 1 theta, alpha n theta. Okay, I mean, the vertex may not be there, but here I'm just saying which direction can I move and still remain feasible. Okay, so this is bi. It's equal to theta if k equals j. Remember, j is that basic column which is entering, and there you just insert the value theta that you have chosen. And it is 0 if k not equal to 0 and k is not equal to j and k is non-basic. So we're not altering any other non-basic column. Only the j non-basic column we had we are adding, but the other non-basic columns still remain non-basic. So clearly, as we had observed in the very beginning of our discussion on pivoting, clearly w theta is bigger than or equal to 0 as xij is less than or equal to 0. So here is where you are using the assumption. So this is true for all I and importantly all theta. So theta, so feasibility is not an issue, and clearly aw theta, the sign constants are satisfied. We just have to check aw theta equals b, but that is nothing but ax naught plus theta aj minus summation I equals 1 to m abi. This is equal to 0 because aj was written as that. Xij's were those coefficients which we use to write aj, this non-basic column, as linear combination of these abis. So this is going to be 0 and ax naught is b. So aw theta is also equal to b. So w theta belongs to f. All right. Now we have to compute the cost. So what happens to C inner product with W theta or C transpose W theta? This is nothing but C transpose X naught plus theta Cj minus summation I equals 1 to m Xij Cbi. So this is the modified cost. We had already computed this, or you can directly compute by looking at what like C transpose Aj looks like and so on. You have to multiply actually this B inverse and then do that. The matrix X, we had proved the result saying X equals this aj1 ajm inverse, we call this matrix B times A. So you can multiply that matrix and inner product with C, and what you will end up with is this is Cj, because this will be the identity matrix. So that inverse times this Aj will be the identity, so you'll reach Cj here, and rest Abi will be converted into this Cbi sort of thing. So anyway, so that's something you can think at your own pace. But we have already done all these computations. This is just the modified cost. Okay. So now Cj bar is strictly less than 0, right? That is, but the way we had chosen j is such that this modified cost was strictly less than 0. So in fact, this is equal to plus theta, something which is strictly less than 0. So some alpha, and alpha is strictly less than 0. So what does that tell us? That by choosing theta to be as large as I want, so C w theta can be made arbitrarily small, not in, I'm not saying in magnitude, but arbitrarily small in the sense it tends to minus infinity, or I can make it as close to minus infinity as I want, or as far away from 0 in the negative direction as I want. Yeah, so this can be made arbitrarily small by choosing theta sufficiently large. Okay, thus LPS is unbounded. Okay, so step 2, we have filled in the gap. So we know how to terminate the program. All right. But still, one issue remains. We are making choices here. So first of all, here we are making a choice. There could be many columns which are strictly negative. So which column should I choose? So, I mean, because it's an algorithm, like I said, we have to empathize with the computer because it's somewhat dumb machine. You have to tell it every single step. Otherwise, it has no idea what to do. You cannot just tell it, okay, just choose one of these. You have to tell it how to choose one of these. Exactly. So, so to so so need a recipe for choice of j, the entering column, and L, the exiting column. Because first of all, j, there might be, like I said, there might be many things in the zeroth row where it is strictly negative, and in the exiting column you have this function. It is like an argmin, right? There might be many values of L such that you have theta naught is equal to xl0 over xlj. So which L should I choose? So I need a recipe for that. So when I implement this algorithm, it will tell it precisely what to do. Okay. And then there is another issue, the issue of cycling. If xi0 is equal to 0, even for a non-basic column, if xi0 is 0, that means it's a degenerate kind of basic feasible solution. What happens to this expression? Here we are saying that I have to choose theta naught so that theta naught is equal to xl0 over xlj. Here the minimum, of course, it has to be positive. I have chosen xij has to be strictly bigger than 0, and all the entries of xi0 are positive numbers because it's a feasibility sign constraint. So what's the lowest theta naught can go? It can go to 0, right? And that will happen if you have one of these xi naughts to be in fact equal to 0. But if theta naught is 0, whatever algorithm that you're suggesting here, you're moving to perturbing by minus theta xij, perturbing by theta, or replacing by theta, and so on. It's like the vertex is not moving. You're not really going to a distinct neighboring vertex. You're just looping back to the same thing. So you might be stuck there. So you might not terminate there. So if xi naught equals 0 for some 1 less than some I between 1 and m, then yeah, by the way, whenever xij is strictly bigger than 0, we may be stuck at a particular BFS. We may be stuck at a vertex or BFS. So these two issues that we pointed out, we'll solve it in one go. So there's one strategy that we will use. It will not only give us a recipe to figure out how to make a choice of the entering column and the exiting column, but it will also solve this issue of cycling. So give us a recipe to figure out how to make a choice of the entering column and the exiting column, but it will also solve this issue of cycling. So that is called the Bland's anti-cycling rule for simplex, for tie breaking. So Bland's anti-cycling rule for tie breaking. So it will break the ties. That's the first issue that we wanted to resolve. And by doing so, it will automatically resolve the cycling issue also. Okay, so what is Bland's anti-cycling rule? So first of all, it's a method to select the entering and exiting columns. That is, it's a method to resolve this first issue I was talking about. So, and what exactly is the method? Method is very easy to specify. What will take us some time is to show that this method actually prevents cycling. Okay. So choose J minimal such that Cj bar is strictly less than 0. Remember, in the tableau, we have these modified costs, and on the basic columns, we had zeros. So basic columns, the modified cost was 0. So in the non-basic columns, you had some quantities. Some of them may be positive, some will be negative. And there might be many which are strictly negative. So out of them, you choose J minimal. So you choose the first, you just keep going. The first time you encounter something strictly negative, you just stop. Of course, I'm not saying that's a great thing, because what might happen is this first time you stop, the negative could be minus zero point 0.1. But perhaps if you went to the next thing, it could be minus 10. So your modified cost, you would faster reach the optimal solution. But so that's why Bland's rule is not really like the optimal rule, but it does the job. It is just good enough. It may not be the best. Yeah. So choose J minimals, and you'll see, notice in the proof that we'll use this fact that J is minimal amongst this Cj bar being strictly less than 0. Okay. And what about L? How do we make choice of L? Choose L for which BL is as small as possible. As small as possible from amongst all those L, from among all L satisfying XLJ strictly bigger than 0, and XL0 divided by XLJ equals theta naught. So theta naught was at minimum over the set Xij bigger than equal to 0 of Xi0 over Xij. So you're looking at all those L's where theta naught equals XL0 over XLJ, and then you're choosing where not L is smallest, you're choosing where BL is smallest. And remember, B is an ordered basis. So what could happen is the ordering could be completely in the opposite direction. So there, the choice you want to make is like if the first one is where you are satisfying this, like in the sense the ordering is this way, then you choose this is the first one. So that is something to keep in mind. So choose L.
Sir, isn't BL J?
Sorry, isn't BL what?
J,
G.
like J.
Yeah, yeah, yeah. No, no, BL is not equal to J. That is not true. So J is a non-basic column. BL is a basic column, right?
Oh, okay, okay. No, I was confused with the previous terminology.
Yeah, yeah. So J is, so choose J. We're trying to choose a non-basic column to add to our. So we're trying to move from one basic feasible solution to another, right? So essentially, we want to remove one of these columns from the basic feasible solution and add a non-basic column which is linearly independent of the rest. So that J is that non-basic column, and L is a basic column for this basis B. Okay. So yeah, so we have to choose L such that BL is minimum, not that L is minimum. Not L itself. Remember, this ordering was important even when we are trying to read off from the tableau what is the basic feasible solution, where to insert zeros, and which way to, like, whatever elements here we had, which way to put it in the basic feasible solution. That was determined by the ordering of this basis B. So that is something that should not be ignored. Okay. So this is the rule. So very simple. You just sequentially go, and whenever you first hit the place where Cj is strictly less than 0, choose that non-basic column. And for basic columns, of course, we have Cj 0. So you'll never really choose a basic column. So J will always be non-basic. And then once you have done that choice, next what you do is move, let's say, L from 1 to M. And as you're navigating this B1, B2, Bm, find the first time you hit theta naught. So that is the L you'll choose. So the hard part or the longer part is this theorem, that simplex terminates using Bland's rule. The simplex algorithm terminates if Bland's rule is used to choose the pivot entry. So pivot entry essentially has information about the exiting column and the entering column, or in other words, entering column and exiting column. All right. So this proof is a bit technical, especially if you're looking at Karloff's book. At least for me, it was very difficult to parse what it was doing. So here is a like simpler way of at least pictorially seeing what's going on. So let's let's systematically split up the proof. So first of all, it will be by contradiction. So we'll use this rule, and then if there is a cycle, we'll start with the assumption that there is a cycle, then we'll reach some contradiction. And I'll point out exactly where Bland's rule is being used. Two parts of the Bland's rule are here, one choosing J and one choosing L. So, and we'll also be very careful and see that. Okay. So assume that using Bland's rule, we fall into a cycle. So assume using Bland's rule, we fall into a cycle. So essentially, you start with this basis B1. So I hope you don't get confused. This B1, so when I write with parentheses, those are meant to be column, but here I'm just saying I have this basis, ordered basis, which I'm changing, and I'm cycling. I went through B1, B2, BQ, and so somehow the simplex algorithm with Bland's rule it brought me back to B1. Okay. So outline. So how will we proceed? First of all, we'll partition N. So we'll partition N, which I recall the definition was just this set, 1 through N. So these were the number of columns, right? Total number of columns was N. And then I'll split it up into some simple parts, some not so simple parts. Okay, so let's think of this as 1 through N. So we'll draw some sort of Venn diagram. And so on. I'm drawing 3, but just imagine there's many of them, as many as Q, right? So all of these bases will correspond to some indices, right? So I'll shade these red. Of course, I have not even told you what this thing is. Bear with me. This region I'll draw as blue, and this region as green. So pairwise intersection I don't really care about. The full intersection I care about, and which could as well be empty for all we know. Okay. So now this red region is what I will call J minus. So it is consisting of all those indices J which do not belong to this union 1 through Q. So these will actually be simple because these never enter into the BFS. So you're taking all the so columns corresponding to J, so corresponding to J in J minus never enter or exit in this cycle. Note that we have a particular cycle in our mind, this B1, B2, BQ. There might be other cycles, but we're starting with one cycle.
Sir, this B1, B2, all of them are like basis.
Yeah, these are all.
Oh,
So this is a so BI. This is an ordered basis, and this diagram is essentially we are cycling through BFS corresponding to this ordered basis. To this ordered basis. That's why I said like there is some abusive notation going on because B parenthesis 1, B parenthesis 2 is representing you have a basis B and you are choosing the columns in that order. But this subscript, essentially if I write B11, this actually makes sense. I'm choosing the ordered basis 1 and I'm choosing its first element, B11, B12, and B1M. And similarly, I can talk about BQ1, BQM, and so on. So I hope that is not too confusing. Yeah. So here, what I'm saying is actually in this particular cycle which we have chosen. I mean, our goal is to prove that there is no cycles if you use Bland's rule, but assume there's some. Then pick one of them. And for that particular cycle, I'm choosing J minus. So in fact, J minus is a function of that cycle. So that is lurking in the background. Okay. So here I'm talking about all columns or all indices which correspond to columns which never enter or exit in the cycle. So those will not play much of a role here, but still we are identifying those indices. And then there is J plus. This is red color. This is everything outside. We don't really care about that as much. Then J plus is all those indices J, which is in the intersection. That's the green region. This also is not that interesting because this column, so columns correspond to things that are always in the basic feasible solution. They are never entering or exiting. I mean, yeah, they never. So here I should say columns correspond to never enter. Okay, I should say never enter in this cycle. So columns corresponding to J in J plus never exit in this cycle. Okay, so what's remaining is J naught. We'll call that J naught. So J says that J belongs to BI1 and J does not belong to BI2 for some I1, I2 in Q. So remember this notation 1 through Q. So for some indices I1, I2, this holds. In other words, these are known as fickle variables. Fickle indices. Fickle meaning sometimes they'll enter, sometimes they'll exit, and so on. So these are fickle indices. So J minus, they will never enter. Think these columns. J plus, they will never exit. Rest are known as fickle indices. So they will enter and exit. Now what I'm going to do is define this quantity, which is max of these fickle indices. So maximum of fickle indices. So this is where the like really things are happening in these fickle indices. The rest are just inert, so there's nothing much to do with them. So in the book, in Karlov, what he will do is he will state in a very complicated way that you have to remove this, that. But anyway, but this is the upshot of that. Okay, so now L belongs to J naught, which means there is a basis B in the cycle such that L exits, because it is fickle, right? It has to exit at some point. So say K enters. So if it exits, something must enter, right? So let's say K enters. And that means B is transformed to B union K minus L. It's just restating symbolically that you're adding K and you're removing L. So in that case, clearly, what can you say about K in comparison with L? That K must be strictly less than L. Why so? Because K is also fickle. Because K was not here and it entered. So it is a fickle variable. So non-fickle are there which do not change their state. Either they're always there or they're never there. But K was not there and it entered. So K is also fickle. But we have chosen L to be the maximum amongst all those fickle indices. So clearly K is less than L, and yeah, K is fickle. K is also fickle. Okay, so now we are going to partition the indices. Again, so there, so here the partition was just identifying which part is important, like J minus J plus are not at all that important. J naught is the one where action is happening. And then essentially we want to partition J naught into parts where we'll try to understand how the modified cost behaves and so on. Now partition indices again into 5 parts. 5 looks like a big number, but in fact, yeah, so what's going on here is K. So K was non-basic. So these are non-basic elements, right? Or indices. K was non-basic, and N was anyway by definition is the set of all. It's like B complement, right? Or J complement, depending on what we use as our indexing set. So K union N minus K just N. So those are the non-basic indices. So that's the partitioning we're doing. So now we have L, and then B intersection J naught minus L, and then B minus J naught. So these are the basic indices. So essentially you're choosing B. So the union of these 3 things is B, right? Anything in B, either it is in J naught, so either it is L, or it is in J naught minus L, or it is not in J naught. It's as simple as that. So union of all this is equal to N.
So what is N?
What is L?
N for Nagpur.
Yeah. So N is non-basic indices. So think of this. You had A1, A2, right? AN, right? So some of these columns are basic columns. So B, so that was J1 through Jm. So those were the basic columns. N refers to the non-basic indices. So essentially you're partitioning N into basic indices, so corresponding to basic columns. And the remaining are known as non-basic indices. Does that answer your question?
Yes, I got it.
Yeah, okay. So these correspond to non-basic columns, right? So and K was non-basic because that entered. I mean, after after performing this step, K will become basic in our new setting. But so far, with respect to B, K is non-basic, and we are just splitting. We are just treating K and N minus K separately. Okay. So yeah, so this is a partition of N. All right. So we start with this vector x, and we get this new BFS by doing these operations, right? So for non-basic things, the indices are all zero. So in fact, not just xn minus k, xn itself is zero. But I'm just splitting it up because I'm also caring about what will happen after I have made these changes, after I have done this pivoting. So start with x, get to x. So by pivoting. So x prime at n minus k is also 0 because these are also still non-basic even after pivoting. But what is different is xk is 0. K was non-basic, but here k has become basic. So xk is theta naught. So for the column that you have added, the value of the basic feasible solution is just theta naught. And xb, so those corresponding to the basic indices, so xb prime is nothing but xb minus theta naught xk. What was that xk? Xk was, so first of all, you had converted, so you started with matrix A. Remember, in our algorithm, what we had done is for those basic columns, we have converted into identity matrix. So that is the one that is called X. And then we had a kth column. Uh, which would enter. Yeah, the kth column would enter. So yeah, so we had this um, the new basic feasible solution would be xb minus theta naught xk. So a and x are related just by that invertible matrix corresponding to those columns. You multiply that b inverse a. So in fact, x was equal to b inverse a, where b was just the padded concatenated columns of a b1, a b2, a bm. Okay. So this is just rewriting what pivoting means. Nothing different going on, but just an extra splitting we have done. So for the common elements in n minus k, we still have 0, but here this change has happened, theta naught. Okay, but to get to x naught, we have to move along a certain vector. So to get from x to x prime, we move in the direction which actually we denoted by alpha 1 theta in the previous proof. So I'm just rewriting that. So we move in the direction d. So let me write it in a new page. So that vector d is 0, 1. So this is like a vector 0, not just an entry 0, and minus xk. Here again, shuffling of indices has occurred, but just think of this as corresponding to n minus k, because you have not moved at all. 0 has stayed 0, so you don't have to change these indices at all. Then from xk equals 0, you have moved by an amount of theta naught to xk. So I'll use this 1 because theta naught times 1 is 1. And then xb, you have moved along this direction, minus theta naught times xk. So I'm just putting xk here. So this corresponds to just the index k, and this corresponds to b, or b, or this, not a script b, or b if you like. This is the indexing set. And note that c dot d. So what is c dot d? So d is the direction in which you are moving. So you're starting with x. So here was your x prime, and this is the direction d in which you're moving. So theta naught times d. So x plus theta naught times d is precisely x prime. So what can you say about CD? You're trying to move to a lower cost, right? Like that's the whole point of this simplex algorithm. When you're moving from one basic feasible solution to another, so this CD must be strictly negative, because in that direction the cost has to be strictly negative. And so essentially you have C of x prime is equal to C of x plus theta naught C of d, which is strictly less than C of x, and theta naught is strictly positive, let's say. So then C dot d has to be strictly negative, right? Okay, so that's the whole point here. Okay, in fact, I think it can also be less than equal to 0. Okay, so if theta naught is strictly bigger than 0, then C dot d is less than 0. And if theta naught is equal to 0, then those coefficients are all 0. So that will be a degenerate case. Okay. So claim 1, that D is in the null space of X. That is XD is equal to 0. So proof. So it's just a matter of reading of what XD will look like. So XD is nothing but, so we look at the corresponding indices, Dn minus k plus xk dk plus xb db, right? So this is 0 because dn minus dn, so d for the indices n minus k is all 0. So this part is 0. So this is 0 plus, now dk is equal to 1, right? So you have xk, dk is equal to 1. And then what is xb? The way we chose our matrix X is so that this is identity. For the basic column, this is just the identity matrix. So this is in fact equal to db. What is db? If we just stare at this matrix, it is db is nothing but minus xk. This is 0. So this finishes the proof of the claim. So D is in the null space of X. Okay. So this is something we have to keep in mind. Now at some iteration, L will re-enter the basis. This is a cycle, remember. So we had split the J into 3 parts, J plus J minus J naught. One, we said it never enters or exits. But if something enters, then it must exit. Like if something is in J naught, it must both enter and exit in a cycle. That's because it is a cycle, right? So if so there must be a first point where it was not there and it entered. Then when you cycle back, there must be a point where it was introduced. So that's why there is always some point where it entered and some point where it exited. So at some iteration, L will re-enter the basis or the column. You can, so this is just a shorthand of saying the column AL will re-enter the basis. Say at basis B hat. So we started with basis B from one of those things in the cycle, and we L exited, K entered. Now we cycle through again. Since after Q steps again L will already be there, so there must be first time L has come in. So that is where we'll call B hat. L will re-enter the basis, say at basis B hat. Okay. Now we'll look at the modified cost function. Now claim 2. Is that if you look at the modified cost function, C bar, this inner product with D is equal to C inner product with D. So the modified cost function, dot D is equal to C dot D. And why is that? Recall what this vector looks like. This is nothing but you take CVec minus, you take the CB. Remember, we defined this as 1 over m vector, or this column vector as a m by 1 vector, where you just had CB1, CB2. There's possible permutation, but you're just looking at CB1, CB2, CBm. So we are ignoring the rest of the entries of the cost function. So this was CB transpose X, right? It was B inverse A, which is precisely equal to X. Now we know D is in the null space from claim 1. So it is as simple as just saying this is equal to C dot D minus CB transpose XD, and this we know to be 0. This is C dot D. So this is what we'll use in our contradiction. So we will show that C bar D is in fact strictly positive. What we know that C dot D is strictly negative, right? Because the cost function has to reduce in this direction. But what we'll show is for the modified cost, this inner product is strictly less than 0, bigger than 0. This will lead to a contradiction. Okay, for that we need some computations. And we will write it in tabular form. Okay, so we have this vector C bar and D. And then we're dividing the indices into this, and we'll note what the entries look like. So these are some column vectors, right? We want to see what the sign of these entries are. So we have partitioned n into 5 sets. So B intersection J naught and B minus J naught. Okay. So we will fill in this table. So let's do that. So 1 for the vector C, C bar. So first claim is C bar J plus is equal to 0. That's because J plus is in every basis. And remember, the modified cost was 0 for a basic column. For a basic column, modified cost is always 0. And since every index in J plus corresponds to a basic column, so this modified cost will always be equal to 0 for everything in J plus. Okay. Next is C bar of L is strictly less than 0. That's because L enters basis at B hat. That's the way we are choosing this B hat, right? So C bar of L at this stage is strictly less than 0. Yeah, so here I just want to point out just one clarification. When we are talking about C, that is the universal cost function. That has nothing to do with the basis. But when we're talking about C bar, this is with respect to B hat, and D, this is with respect to B. So that is something we have to keep in mind. So it's not the same B. Okay. So this takes care of the yeah. And by the way, like everything in J minus we don't really care about because they don't contribute to the cost, because the xij's or the entry of the optimal the basic feasible solution x will be 0 corresponding to those coordinates. So the cost function, whatever be the value, it doesn't really matter. Okay. Now let's look at Fickle indices. So now C bar of J naught intersection B hat is equal to 0. So this is for all indices in B hat. So why is that? What is J naught? Yeah, so in B hat, this is a basic column. So J naught is all those Fickle indices, and B hat is the new basic. Okay, now I think we have to be a bit careful here. So J naught consists of all those Fickle indices. Right. Yeah. This has nothing to do with J naught per se, because C bar B hat itself is 0, because those are corresponding to the basic columns. And L has entered into the picture here. Okay. So the next is C bar J naught minus B hat union L. That is bigger than or equal to 0. Okay, so what exactly is this set? You're taking B hat union L. So B hat, recall, is, what's B hat? I think we defined it. At some iteration, L will re-enter the basis. L was the maximum of all the Fickle indices. So you took B hat. Right. I think I should clarify here something. Otherwise, this won't make much sense. So when I define B hat at some iteration, L will re-enter basis. What I mean is L does not belong to B hat, and L belongs to successor of B hat, let's say. Meaning, like in the cycle, there is a successor of B hat. L belongs to successor of B hat. So one thing to note is L does not belong to B hat yet. So that's why otherwise this statement wouldn't be very interesting, right? You're taking union with something which is already in that set. Okay. So now you are ignoring things in B hat and also things in L. Okay, so why is this bigger than or equal to 0? So this is because of Bland's rule. So here, until now, we have not even mentioned Bland's rule at all. Okay, let's see. So Bland's rule. So it talks about how L will enter, right? So at L, you will have C bar of L is strictly less than 0, because otherwise how will L enter? L is that non-basic column where cost is strictly less than 0. But if for a lower index than L, um, if you had something which is strictly less than 0, then it will violate Bland's rule, because you are choosing something which has the lowest index, and the cost is this modified cost is strictly negative. That's why for all these fickle indices which do not contain this b hat and also do not contain L, we have C bar J naught is bigger than equal to 0, because then otherwise you will not really, L will not re-enter this basis. Something else will re-enter the basis on like using Bland's rule. Okay, so because of Bland's rule, we have this. So putting this together, you have C bar of J naught minus L. So union of these two sets. So this is all fickle indices outside of L. Okay, so these are all fickle indices outside of L. So let's try to fill in that this column. So what happens with C bar K? So that's a basic column. No, sorry. So K, yeah, K is in J naught minus L. K is fickle, so it is in J naught. So it is in, so it's bigger than equal to 0. So C bar here, it is bigger than equal to 0. N minus K, I'm not so sure. We have not really found out. But as we'll see when we take C dot D, note that at the n minus k entries, D has zeros. So when I'm taking inner product of these two vectors, it will not matter what is here. It will just contribute 0 to the whole thing. Now, what about L? What is C bar L? Here we have seen C bar L is strictly less than 0, because L enters basis at B hat. So the successor of B hat will contain L. So this is strictly less than 0. Now, what about B intersection J naught minus L? So this is bigger than equal to 0, same as the first. Because B, whatever, it is containing all fickle indices, not containing L. It's a smaller set than that. If I forget about the B, it's still bigger than equal to 0. That's what we proved here, right? So even if you intersect with B, it will still be true. Now, what about B minus J naught? This is actually exactly equal to 0. Yeah, is there a question?
No, sir. I just told it's 0.
Yeah, right. Yes, thanks. So this is actually precisely equal to 0, because yeah, I mean, it's outside of J naught. It's a basic column. So as simple as saying it's a basic column of B hat, and it is not containing the fickle indices, in particular L. So yeah, it is equal to 0. Now when I take, okay, now I have to fill in the entries for D, and then I'll take the inner product to bring out the contradiction. Now dk is equal to 1, bigger than 0, and dn minus k is equal to 0. So remember, it was looking something like 0, 1 minus xk, and this corresponded to k, this corresponded to, sorry, this corresponded to n minus k, this was like k, and this corresponded to b, right? So these two parts are easy to check. So let me fill in these entries. Dk equals 1, dn minus k is 0. So like I said, when I'm taking inner product, whatever is in here doesn't matter. And as you can already guess here, if I'll just put a question mark, because it doesn't matter what I put here. B minus J naught, the entries of C bar are equal to 0. Okay. So now, so Bland's rule has two parts, right? We have used up one of these parts. So which part did we use? Here it was the choice of the entering column. So L was entering in the successive choice of ordered basis after B hat. So that is the part of Bland's rule we have used. We still, I mean, if you didn't use the second part, you'd feel suspicious that like something is wrong with this proof. Okay, So this is where the second part of Bland's rule will come into the picture. So dl equals minus xk uh, minus xrk is less than 0 for some r equals 1 through m. So what exactly is L? L is the rth basic index with respect to B. So not B hat, with respect to B. So that's why I tried to clarify. Don't think it's the same basis when we're talking about C bar and D bar, the D vec and C bar vec. But when this claim we're proving, we're consistent with that. So it's not like we're like hand waving our way through some non-related claims. So even when we're making this claim, here D is with respect to B and C bar is with respect to B hat. Okay. All right. So DL is equal to minus XRK is strictly less than 0. And here L is in fact the rth basic index. So in fact R I can, so R is equal to BL. No, or rather it's opposite. So L is equal to BR. Okay. So now theta naught is equal to minimum of bi over xik. K is the basic column that has entered. So when you're talking about the basis B, and L has exited. So k is fixed, and you are maximizing this over all the xik, which are strictly bigger than 0, and I is between 1 and n. Now this implies xrk. So I'm trying to give a reasoning for this. So this implies xrk is strictly bigger than 0. Yeah, sure. I mean, so this set was non-empty. So you're just choosing like the entry to be xrk strictly bigger than 0. Yeah. So this dl is in fact minus xrk is strictly less than 0 because of this fact. So whatever I have written in parentheses is a justification of this. dl is equal to minus xrk is strictly less than 0. So let me fill in this. So this is strictly less than 0. So the strict inequality here is important. Okay. So now we want to talk about d of b intersection j naught minus L. Now assume that dj is less than equal to 0. So what I really want to show is this entry will also be bigger than equal to 0. Till now I have not shown it, but essentially if I want to build a contradiction, I want to take this inner product and show that it is strictly positive. And we already know that this is C dot D, either it is strictly negative or it is 0. It's less than equal to 0. So that's the contradiction I want to build. So working backwards, I guess you can already guess that I want to show that this is bigger than equal to 0. So all the entries of D corresponding to the indices B intersection J naught minus L, uh, yeah, are bigger than equal to 0. Okay. So if dj is less than 0, then j is in B, right? Because if you look at this D, so you have 0, 1. If it is strict, here 0 and 1, like this is 0 vec. These are all like non-negative numbers. So if it is strictly negative, then you have to belong to one of these basic indices. So then j belongs to B. So let's say j is sth basic index. So this will imply dj is nothing but minus xsk, which is strictly less than 0, which implies xsk. So here we are going the opposite direction. Here we showed that xrk is bigger than 0, hence dl is less than 0. Here we're going the opposite direction. We're saying if dj is less than 0, then xsk is strictly bigger than 0, for s being the index which determines J. Now, since J belongs to B intersection J naught minus L, this implies J is strictly less than L. Okay, so why is this? Hmm.
Because L is the maximum of all the
Right. Exactly, right. So it's a fickle index. So L is the, yeah. So L is the maximum of the fickle indices, or J cannot be equal to L. So J is strictly less than L. And this implies Bs is strictly less than Br. So L in our previous notation is Br, and J is in our present notation is Bs. But then, so in this ordering, Bs is strictly less than Br, and XSK is strictly bigger than 0. So Bland's rule, the second part of Bland's rule, should not really have chosen Br. So we should not have chosen L to enter the basis. Rather, we should have chosen J to enter our ordered basis. So simplex plus Bland's rule would have chosen S instead, or rather Bs. Like if you're thinking purely in terms of what column to choose, the column Bs. And this is where it's important, like you said, when we say minimum of this L, we're talking about like minimum of BL rather than L. So so BS has to be minimum rather than S being less than R. Okay, so we would have chosen S instead, contradicting our choice of R. So there's a layers of contradiction going on here. So what this means is this fact is not true. So dj must be less than dj must be bigger than equal to 0, and we have filled out our table. Yeah, so we have filled out a table, and this means C bar D is strictly bigger than 0, because there is one entry where both are strictly less than 0. So the product is going to be strictly bigger than 0. Whereas C dot D is less than equal to 0. So another like contradiction of our very original hypothesis. So this shows that Bland's rule will prevent a sort of cycling from happening. Okay. So now what remains in the tree? So let me redraw that tree. So the tree was, we had this linear program, infeasible. So when will this program terminate? So if it is infeasible, or you find a basic feasible solution, and then you say unbounded, or then you go to neighboring BFS with cheaper cost, and then you loop around, and if you terminate if cost cannot with strictly cheaper cost, I should say, if cost cannot be cheaper, strictly cheaper. So now what remains is to determine, first of all, whether a LP is feasible or not, and if it is, then finding a basic feasible solution, because that is our starting point. So that's what we'll do. So getting started. All right. So yeah, I mean, so you have x bigger than equal to 0 and ax is equal to b. So first question we want to answer is whether this is feasible or not. So what we do is, like before, you first try to solve this equation, ax equals b. So here itself, if it is infeasible, then you don't have to care about the sign constants. So one, if ax equals b is infeasible, declare infeasible and terminate. You don't care about the sign constraints. So this you can do just by reducing it to like a row echelon form and directly reading off whether there is some contradicting terms. Like you have a row of zeros and the corresponding entry in B is not zero. And terminate. Okay. Now if it is feasible, we'll add some dummy variables. So to add m, so m is rank of A. So we have already seen that if it is feasible, then you just remove all those dependent rows, and so you can always assume rank, like A has full rank. So add m artificial variables. So let's call them x1 prime, xm prime. Or in other words, let me just redraw the matrix. So you have this m by m matrix. So 1, 0, 0, 1, 1, and you're padding it with A. And here is where I'm introducing the variables x1 prime, x2 prime, then xm prime, and then your x1, x2, xn will start. So m plus n variables. So you have added these dummy sort of artificial variables. And you want to solve it for this equals b. And you still have the sign constants. And xi prime is bigger than or equal to 0 for 1 less than or equal to I less than or equal to m. And xj bigger than or equal to 0 for 1 less than or equal to sorry, yeah, 1 less than or equal to j less than or equal to n. Without loss of generality, we can assume actually b is a positive vector. That's because we can just modify, like you can multiply, if b has a negative entry, you just multiply -1 to that corresponding row. Then you are just modifying the matrix A and ensuring that the solution space does not change. Just the entries of B become positive. So without loss of generality. We may assume B is bigger than or equal to 0 by modifying A. Okay. So with that assumption, so we need this lemma. So this is a new LP in standard form. So we have a new linear program in standard form. So the lemma says the new problem has optimum value 0 if and only if the original problem is feasible. The new problem has optimum value 0 if and oh, by the way, I didn't even define what the problem is. So this, so minimize summation I equals 1 to m xi prime. So this is the problem subject to these constraints. So this is the new linear program that we have constructed. So the new problem has optimum value 0. That means since because of the sign constant, it's just saying that all these x1 primes may be assumed to be 0. So if and only if the original problem is feasible. Because if I have a set of x1 prime, x2 prime, and all the way up to x1, xn prime, where it has optimum value 0, that means all these entries x1 prime, xn prime, they're all 0, which means rest of the x1, x2, xn, they must satisfy all the constants that we need. They'll satisfy the equation ax equals b and also satisfy the sign constants. All right. So one direction is clear. Like if the original problem, if the optimum value of this new problem is 0, then the original problem is feasible. What about the other direction? So what about this direction? That if the original problem is feasible, yeah, right. Then you just put in x1 prime, xn prime, all of them to be 0. So that is definitely feasible. And it has to be optimal because these are all non-negative numbers. Okay, so both directions are pretty straightforward. So not much to do there. But then what have we done here? We have essentially reduced one problem to another problem. So here we are claiming that original problem is feasible if and only if optimum value is 0. But again, for this new problem, we still have to go through the tree. For the new problem, new linear program, we have to see whether it is feasible or not. But that is actually easily checked. So the new LP uh, so is feasible and has a BFS. So not only it is feasible, you can actually get a BFS immediately. So the BFS is B1 through Bm and the rest to be 0. So in fact, in the tree, not only do you conclude it's like feasible, but also you actually find a basic feasible solution. So why is this a basic feasible solution? For that, we have to check whether it's a vertex, right? So now, whatever entries I choose, like x1, whatever vectors I choose, let's say x plus y over 2 is this vector b1 through bm and zeros. So these are all, they must satisfy sign constants. And if average of two positive numbers is 0, then both the positive numbers must be 0. So both x and y, they must satisfy 0 in these parts. But they also have this condition where ax is less than equal to b1. And ay is less than equal to b1. So if the average is equal to b, then ax must be equal to b and ay must also be equal to b. So that will tell you that the first m coordinates must also be, because when we're talking about the a, that is this bigger a, this is the identity matrix. So it's essentially just telling you that the first few entries must also be equal. So in fact, that means this is a vertex, and we have checked that vertices are in fact basic feasible solutions. Or you can just directly say I'll choose these basic columns. So this, if I choose 1 to up to m, these are linearly independent columns of a new a. So corresponding to that, I have a positive solution, like a feasible solution, which is basic. So it must be a vertex. All right. So this new LP we can directly read off a basic feasible solution, and then you do the simplex algorithm to find the optimal value. Now, if optimal value found, so if optimal value of new LP is strictly bigger than 0, report infeasibility and halt based on that lemma. And then third, use simplex. So once you have found this basic feasible solution, or rather I should say, if you have found a feasible solution, then you find a vertex using something which we did actually even prior to simplex. I had written a pseudocode in class, if you remember. So from a basic, okay, no, so that's one way to proceed. The other way is to actually show that if okay, so if the original LP mm, okay, so if X is a BFS of new LP, then X1 star, Xn star is a BFS of original LP. So what I'm saying is, if you find a basic feasible solution of this new LP, what you can do is just focus on okay, so is an optimal, I should say, is an optimal BFS. So let's say you found this optimal basic feasible solution of this new LP, then you just ignore all the terms corresponding to x1 prime, x2 prime, xm prime. So you're left with n things, right? Then if you just take those n things, there must be a basic feasible solution of original LP. So I'll leave this as an exercise. So then you get a vertex. Once you start with a vertex, now you know, like now you started. Now you can think of what basic columns to add, how to pivot, and so on. Okay, so this is just step 3. So this pretty much finishes our approach to solving linear programming. And the only thing that remains is talking about performance. So the worst case performance typically will be exponential. As I had mentioned, that if you do the brute force method using those Dehn-Somerville relations, I had mentioned that if you have like the number of vertices can be exponentially large, um, like in terms of the number of linear inequalities that you give to define a polyhedron. So in that sense, a brute force algorithm is also definitely exponential. But it turns out even the simplex algorithm, the greedy algorithm, so to say, locally you're going to the cheaper vertex nearby. Um, so there also you can have like exponential complexity. So the example I'll just repeat from the book. So let's say you have this problem, maximization problem, xj subject to 2 times j equals 1 through I minus 1, xj plus xi less than equal to 100 to the I minus 1 for 1 less than equal to I less than equal to n, and xj bigger than equal to 0. So this as a function of n, like if you got unlucky and really started with the wrong basic feasible solution, it can take you up to 2 to the n minus 1 points. You might have to navigate until you find the optimal solution. So here, if we pivot by choosing the entering variable so that Cj bar is most negative, which is not necessarily the one following Bland's rule. Bland's rule just says the first negative thing you encounter, you go in that direction of that neighbor, go to that neighbor. But if instead you decided to go with the neighbor which is most negative, then you'll have to traverse 2 to the n minus 1 points. Okay. So this is where I would like to conclude. This is a very nice point to stop. So next class, actually, we'll start to talk about some computer programs and like Python, like modules